I'd like to introduce myself. My name is Paul Craig, Chief Developer of the EFDC Explorer Modeling System. Thank you for taking the time to participate in this webinar. What we're going to be doing today is starting off with a brief presentation of the tools, and then a live demonstration of the actual model build process. I do apologize up front for my cold, and I will try to mute the mic as best I can before I cough. Anyways, but let's go ahead and get started. So the EFDC Explorer Modeling System is this framework that we have developed here at DSI, including the CVL grid, our grid generation tool, the EFDC Explorer, which is the pre and post processor, and then the computational engine of the work is the EFDC Plus code, plus because it has many enhancements over the original EFDC code. And fundamentally, it's like most pre-processors and post-processors, EE can digest a large amount of material from different formats and types of data, that it brings it into EFDC Explorer, which in turn then processes those data into the necessary files that EFDC actually needs to run, and then it'll save those out. You can run the model, and then this is an iterative process here where you run the model, analyze the results in a post-processing effort, and then go through the calibration. So we will not be looking at this in a calibration mode today. We will simply be building the model initially. So, we are focusing here on this estuary, the Khuc estuary in Vietnam, and we have provided all the data files and everything necessary for you to duplicate this process at the end of the webinar. So you can go to our website, download the files, and follow the example more directly if you desire. So also at the end of this webinar, we will be sending out a link to the webinar to all the participants. So we're going to be focusing today on just hydrodynamic model setup. So what we're going to be stepping through is bringing a grid into EE, assigning bathymetry, water surface elevation, bottom roughness, assigning our boundary conditions for flows and water levels, and then linking those time series to the appropriate location in the model domain, making our hydrodynamic settings, running, and then, of course, like I said, we're not really calibrating right now, but we'll iterate through this process quickly, and I will be moving relatively quickly today so we can get to the end so that we can have plenty of time for question and answers at the end of the webinar, or at least the formal presentation portion of the webinar. And then actually, once we finish the hydrodynamics and we'll run a quick test of the model, we will add salinity and go multi-layer, and we'll step through that at the very end. So this is the model domain. The background image was saved out, and you can bring it into the background. This particular tool that you're looking at here is the CVL grid, our grid generator. So we generated this relatively simple coastal grid with open ocean boundary out here, and then there's a tidal inlet here with a sand spit coming up from the north and the south, and then a river flowing in through this reach, just as a demonstration. So with that, as far as a brief introduction to the model, let's step into the actual live demo. So this is the user interface for the EFDC Explorer modeling system for the pre and post processor, EE. And what we're going to do is generate a new model. So we look here at this first toolbar button. It says generate new model. We click on that, and that brings up this dialog box here that you see, and we have a range of different options. We're not going to be covering all the different available options. That's more in a training document, but we can generate Cartesian grids. We can import various kinds of grids. But in this particular example, we're just going to load up the CVO grid here that we have already generated. So I'm going to browse here to a file that contains the already developed CVO grid file. So we've saved all this, and as I mentioned, you can obtain all these files from our website if you want to follow the hands-on examples yourselves. So I'll go to the grid. There's the Khuc CVO grid file. Select that. Now the next thing you need to do is essentially just kind of define some preliminary initial values. Now the reality is that all of these variables can change later. You have a robust capability of making changes to any of the initial conditions and boundary conditions later. But just to get the model started up, these options that you see here for channel roughness in the Z0, which is the units of these are in meters, water surface elevation, bottom elevation, and while we have additional options here under the bathymetry, I recommend that you always just use a flat bottom initially and assign the a flat bottom for this first step. So with that set, we click on the generate button here, goes out and creates a model domain with 2,204 cells. This note here is just simply this because there are some very complex grids out there where you have a lot of very tortuous water bodies, and sometimes it gets a little confusing as to what is the I and the J basis, and this is just reminding the user to check it, make sure that it makes sense, and if it doesn't, then you have some tools here to adjust your I and J map in the EFDC model. But with this said, hit OK, and you can see here that the model has been generated, and we have the grid, and this particular map here just shows a quick view of the grid, and then we can look at we'll just keep it on map, and you can see we've got 2,000 cells. So with that, we will move on to now beginning to assign some of the initial conditions that are needed. So to do that, let's go here to the domain tab. Go to I'll just click here initially on the grid tab here. So on this grid tab, you can see that right now we're just using this, by default, it's a single layer model. So we're going to click on the initial condition and bottom roughness tab, and we're going to just follow the order in which these are displayed here. We're going to assign bathymetry, then depth or water surface elevation, and then bottom roughness. So to assign bottom elevation, just click on the bathymetry, the assign tab here. Now this is a very common form that we use for a lot of our spatial assignments for different types of properties. And depending upon what is being set, in this case bottom elevation, as you can see here, because bottom elevation was selected, we have options down here that apply to bottom elevation. You'll see later when we're doing water column or other things that these options vary, but the form basically looks very similar. The concept between a poly file or a polygon file and a data file are a polygon file tells EE if you specify one, it will only apply this initial condition assignment that we're getting ready to do to only the cells that are inside that polygon. So I'll just browse to this for now. Let's jump to data. And we have provided here, and you'll be able to have access to it, a domain.p2d, and this is just a simple, the p2d file is a open with, no, never mind, we'll just, it's a simple ASCII file. So, with the XY values in ordered pair so we can get a polygon. So with that selected, then you have different options down here for how you want to set your bathymetry. The two main ones are the interpolate data and the average data. Interpolate data generally is applied when you have relatively sparse data compared to your grid resolution. So if you just have a few data points scattered throughout the an estuary or a lake or something, and you want to just generally apply a bathymetry, you would use interpolate data. But the average data is more. This is used when you have high resolution data relative to your grid. As an example, so you have multi-beam data, and you may have millions of data points. And within a single cell of your hydrodynamic model, you may actually contain thousands of data points inside your cell. So anyways, that's the concept here, and it can range from, the number of points inside a cell can range from 1 to a very large number. However, there may be a case where there are data that you may have high resolution data most places, but you may miss a few cells, let's say along the edge or in some special condition where there was no data actually collected. In which case, then you can use this sub option here to allow you to interpolate any empty cells. So these two together pretty much provide a really robust ability to assign initial condition bathymetry when you have high resolution data. And then you can constrain whether or not you want to raise or lower, but typically you're just going to use both, and it'll raise or lower the bathymetry from the existing values. So with that set, well, I haven't set my bathymetry yet. So I need to point to the bathymetry file. Again, data folder down here under initial condition. Where is it? Bathymetry. So this file is the entire domain polygon, and then this is the the bathymetry. So with that set, I hit apply. You can see it's reporting back here what it was doing, and now finished. It has set the bathymetry for all 2004 cells, and go to done. Now we can just march through this if we want, but if at any time during the model generation process, you can always look at the 2D plan view. So this is the 2D plan view, the 2D vertical slice, and the 3D view of the model. So right now, let's just look at the plan view. So there's the model domain. Turn off the grid, you can see the bathymetry shown there. So with that, looked okay, made sense. Let's go ahead and assign now to the water depths. Now this one, I could, again, specify the full domain, but because I am assigning the water surface elevations for the entire domain already, it doesn't really matter if I specify this file or not. If I don't specify it, then it's just going to apply this XYZ data file to the entire domain, which is what I'm going to use here. So here I'm specifying the water surface elevation file. Here, under data, IC, water surface elevation. But now notice that this is a different set of options below. Typically you're assigning elevations, but you can optionally just assign depths if that makes more sense in your application. But most real world examples, you're actually assigning a water surface elevation value. So with that, those set, and this selected here to point measurements, I hit apply. And you can see here again, it's working, it finished. So now I have assigned bathymetry and I've assigned water surface elevation, which of course, from which I get depths. So if I look here at the 2D plan view now, and I go to water levels, you can see now we have elevation and depths. But one of the problems that you will see here is that I have basically the river flows through this reach, and I have water essentially mounded up on the sides of the channel, where the cells, the land is actually dry at this elevation. And the reason why it displays this way is because we simply haven't turned on the wetting and drying option. So to do that, let's just go ahead and turn on the wetting and drying. Come in here into hydrodynamics, select use for the wetting and drying option here. Now you can change this. Dry depth is in meters, so this is a 5 centimeter dry depth. And essentially what happens, the EFDC turns on and off a cell based on its predicted water surface or depth at that cell. So if it's less than 5 centimeters, the cell is dry and is deactive for the rest, for all transport and kinetic processes. If it's greater than 5 centimeters, then it is active. So with that said, let's now look at what the water surface elevation plot looks like. And now you'll see here in this example that we now have water surface elevation, that's depths, excuse me, water surface elevation plotted up, nice, smooth within the main river channel itself, moving out into the ocean. And these gray cells represent dry cells. You'll notice up here when I click on a cell, it gives me the depth, and since they're up here on the side of the hill, they are assigned an initial value of 90% of the dry depth. So they are effectively inactive during the initial, during these lower flow simulation processes. So that's how you kind of apply wetting and drying to within EFDC. So with that set, now let's go back to the domain and set the bottom roughness. So again, I'm going to ignore the polyfile and just point to initial condition bottom roughness file here, use gridded data, and apply. All right, so with that set, now let's look at the model a little bit more. Let's do a few things here. Let's turn on the horizontal scale here so you can kind of get a sense of the scale. And I always do this a little too fast. To get access to the display options for the 2D plan view option, that is this toolbar button here, this display options, or you can optionally just click on the scale here, and it will bring up the display options. And with that displayed, turn on the legend here. So now we can see here, we've got depth ranging from basically 50 or 5 centimeters up to about almost 19 meters in depth in the system, and there's our water surface elevation. So now the next thing we need to do is save the model. I recommend that, you know, just periodically during the model construction process, you can save the model and do it as frequently as you need to. So I'm going to click on the save button here, save it out. I'll just create a demo 1 example here. So I'll save it out. Now, this model has now been saved. Let's look at what's in that directory. So I can come in here to the tool or the toolbar and go to the input edit option here, select other inputs. So these are the files that EE automatically generated based on the current settings that we have set thus far. So this is the primary control file for EFDC, and yeah, EE knows exactly what needs to be saved, which files are needed when it saves out the model, and will save all the files that is needed by EFDC. So with that said, we've got the bathymetry. Well, actually, let's go back to the plan view so we can see some of the other processes that are going on here. Go to, so we have the bottom elevation. I can look here at the fixed parameters, and there's my bed roughness that I assigned. So out here in the ocean, 1 centimeter, in the main channel, 2 centimeters, and up on the dry cells, a 3 centimeter bottom roughness. So with that set, we now have the model basically configured for the initial conditions for the simple hydrodynamics. Now let's go ahead and begin to define some of the boundary conditions. So to do that, we can do it a number of different ways, but we're going to take this approach here. Go to the domain tab, boundary conditions, and then down here in this frame here, it lists all the currently defined boundary forcing time series or boundary forcings that the EFDC model is currently configured. And as you can see, they're all 0 right now. But what we need to do first is, excuse me, what we need to do first is define the flows here. So just by clicking on this E button here, this will edit the flow series. It'll bring up the flow form here. This is a standard time series editing form used for all the different types of time series that EFDC needs. So at this point in time, let's go ahead and specify the number of series. This is the maximum number of series that the EFDC model needs, and you can change this at any time. You know, you run the model and you want to add another time series because you need to add a new boundary condition. You just, you know, raise this number up to a higher number, and, you know, then you can add time series, or you can just make this, you know, lower it, and it's going to delete all the time series greater than the number that you entered up there. So in this case, yes. So we've got one time series. So that's all we have in this example. So I'm going to import the data, and these data have already been provided. So I will browse to those data again here under the data folder. We have the BC flow data file. So that's what we're going to load up now. So you'll notice here, if this is selected, I don't really need to worry too much about these parameters down here, but we will later. I'll show you why, but because this particular format is kind of predefined, so EE knows how to read these data. If I want to see what's in those data, I can hit the preview button, and it goes out and loads that data file and just previews it. And you think, okay, that's what I need. So I'm going to just go ahead and say okay and accept that. Now the next thing is EE is going to try to split those flows into the layers that is currently defined in the model. Well, in this case, we only have one layer, so really it doesn't really matter, but just the default is -1, which evenly divides the flow that you're importing into each layer. But we'll just set 1. So there's the data, time in this column, and flows in this column. The number of decimal places is referred to as the precision here, and we just want, let's just go with typical value is more like 3 for the time. That allows you to get down to sub-hourly time steps with no problem. And then in this case, flows were just the nearest one is fine. So there's our time, and this time is in Julian days. And we'll talk about kind of what that means as far as how to link that to a calendar date a little bit later in the demonstration. So with this imported, and then I can come over here to editing tools, and I can edit these with operators and do different operations on this. But we use this file tools and imported the data to get this file. Now, the last thing I want to do is I just want to give it a name. So this is the river flow, some name. So this allows you as the user, when you're looking at your boundary conditions, you can link that, oh, series 1 is actually this river flow. That's set. Well, I could hit OK, but let's just go ahead and use the view series right now. Just hit current. And you have two different options here. Well, you can specify the date range that you want to extract for your view, or you can hit runtime. And if that you've got that selected, it'll just display the actual model configured runtime. But we haven't configured the runtime yet, so I'll just leave that blank, hit OK, and there's the entire year plotted up. And you'll notice that now this is a calendar date down here, and that's, again, I'll talk about that later, but if you want to look at it in Julian date, you can just toggle between calendar and Julian here. So with that set, say OK. We now have a defined flow boundary. Now we need a defined, well, a boundary series. Now we need to define a water level series for our ocean boundary. To do that, again, you click on the edit button here, tell it how many series you want, and then under File Tools, we will import data. And here what we want to do is these data are actually Julian date and value, date time stamped. So we will point to boundary condition water level data here. And then you'll notice here down in the first line of importing that it shows that this is actually a text, and that doesn't really apply. And when it tries to convert that to date time, it doesn't work. Well, we need to put a skip on the header. So if you skip the top row, this is the first line of the data in that file. And so if I want to now, I want to bring in column 2 that, and now you can see that this has been updated, and that is indeed the date time stamp that I want to use. Preview that data. There's our title series that are included in that file. So with that set, say OK. Now that this is the same data, I can again plot it up here. There's the data. And we'll call this ocean. Say OK. We now have a defined tide series. We have a defined flow. But what we haven't done is we haven't actually told EFDC how to use these data. So we haven't linked these series to the appropriate cells in the model domain. So that's what we're going to do next. So there's a number of ways you can do it. You can use this tool here and add boundary conditions. Now this is a very important concept that EE manages a boundary condition by a logical or physical group. So in other words, let me just close this out and go to the 2D plan view. And then we'll go to the boundary condition tab, turn back on the grid. So you can see here, we have the grid. Well, this is the ocean open boundary. And depending upon how sophisticated your model is, you can have, you know, a range of different options for addressing this. But we're going to assign this whole group of cells here to one series because we're just saying that they all behave similarly. And then we're going to assign a rivers flow for a single discharge series that we have into this upstream area here on the model domain. So to do that, excuse me, let me just show you here. We've got a couple of data file or predefined files for you here. We call them self-selection OpenBC and RiverBC. So I can just drag these onto the 2D plan view, and there it is there. So you can see the river selection polygon is just this line that cuts through those cells there. And then likewise, I want to do these cells, so I just drag in the ocean. So I'm only doing this so that you can see these polylines, but they're not necessary to be displayed to be used. So now what we're going to do is we're going to go ahead and create a boundary condition for well, let's start with the river here. So way to do it is this is an option to enable edit, or it's just a protection to keep the user from inadvertently changing results. But if we come over here and just right mouse click on any cell in the area and click on new, we're going to create a new group. And what we're going to do is manage the river flow coming in for all the cells in one group. So with that, I'm just going to call this river and say OK. And then I have to tell EFDC what type of boundary it is. And these are the options that are available to EFDC Plus. We have a flow boundary, which is what this is. We can also define it as a hydraulic structure, including both a flow table as well as flow equations. We've got the open boundaries, and then withdrawal return type boundary, and a jet plume, or like a thermal discharge. So in this case, we're going to just specify one for a flow boundary. And this is the group form. And you can see here, currently in the group, we only have defined one cell in this group of named river of type flow. But what I want to do is add all these cells, and I could manually type, hit add cell and type in, and add cell and type in, but it's a lot easier just to add by polyline. So if I click on that button, then I browse to that cell selection River BC file here, hit apply. Now you can see we've got 17 cells that are currently defined in this group. And each cell, as I scroll through the cells here, you can see information over here about what the cell is. So this is the L index, and then the I and the J as you scroll through here, and then it tells you what the initial depth is and the bottom elevation, etc. This is informational on this. The black frame with green text is informational. You can't edit that, but we could directly edit these, but there's no need to. We use the polyline approach to define these. So this is set, but now we need to link the time series that we define for the river flow to these cells. And you do that right here under the table. Now this is important to note is that the flow assignment for a boundary type is on a cell-by-cell basis. So each cell could use its own time series, but we don't have to do that. We right now we just have one time series that we want to apply to all of these cells. So you can see as I scroll through, it's still saying none, but then when I get to the one cell that I assigned, now it's a set. If I want that to apply to all the cells, I just hit all right here. Now all 17 cells are using that flow file. However, if you remember, we've got, this is a floodplain, and we got a main river, and we got overbank channels, and some of these cells are actually dry. So if I come over here to the side, you look over here, the bottom, the initial depth is 4.5 centimeters. That is essentially a dry cell. So there's what you do with the EFDC is you apply a distribution factor. So I have a single discharge, but then I split it on a cell-by-cell basis based on the cell size and depth. So I hit distribute factor, and now you notice that this particular cell actually gets no flow. And then as I scroll down into the main channel, these cells are all getting flow, and now no flow again on the other side of the channel. So we have now linked this flow series to this group of cells, and we'll talk about this later when we got about salinity. So I'll say okay. So we now have, I zoom in here, a group of cells that define this current flow boundary. Now we're going to do the same thing. I'm going to press Control E to jump to the full extent, and I'm going to define the open boundary for the ocean. So go to new, this is ocean, give it a name. Now this, we'll talk about a little bit if I have time about the difference between the different open boundary groups, but the east, west, north, and south all refer to the cell map direction, not necessarily a physical direction. So these are actually all considered the east boundaries. So we're going to call this 4 and define these group of cells as a boundary condition east. Say okay. Similar form now. Again, we're going to add the rest of the cells by polyline. Grid data, cell selection ocean, apply, goes out, finishes. There's 42 cells identified for this boundary condition. Now, likewise, just like the flows, each cell can have a unique pressure series or a harmonic series or a combination of these two applied to each cell. But we just have one series, so I'm going to apply that one series that we have previously defined called ocean, and then I'm going to do a set all here to set these settings that you see here to all the cells based on the current cell settings. So set all. So now as I scroll through, you can see they've got the pressure series set for every one of these cells. And then I'll go ahead and just define the number of time steps for smooth transition. One other thing I'm going to do, and this gets into a more advanced topic, but we can just, if you select this, flatten the two internal cells, there are some numerics within EFDC that make it more stable. You get better results at the boundaries if you're near boundary cells for open boundaries are flat. So I'm going to just flatten the two interior cells to the same surface elevation, bottom elevation on the edge. And that is all we'll apply at this point in time. So now you can see here I've got the E for the east boundary, and then I have my flow boundaries here. And if I'm going to turn off these lines here, and I do that right here with display options, go to annotations. And I can globally just turn everything off there, or I can scroll through and turn off each layer that I've loaded up as separate here, but I'm going to globally turn them off. So you'll notice the lines are gone now. So we've now defined, we've got a bottom elevation, water surface elevation, bottom roughness. We have our boundary conditions assigned. We're not going to deal with wind and atmospheric conditions in this training here. But with that set, we have the fundamentals of the model configured right now. So now what we want to do is go ahead and set up the timing that we want to use for the model. So to do that, we come down here to the timing tab. And here, this is in Julian days, the time of start, and then the number of reference periods. And this, by default, it defined a reference period of 24 hours. So that's 1 day, and that's a common. But you can make it as large or small as what makes sense for your application. But we typically just do it in reference periods of the 24-hour period. So I'm going to simulate 10 days. So I just put 10 days in there. Now, I also want. We have a couple of different options here on how we're going to solve the model. By default, I'll just come here to the hydrodynamics tab. We're using a 2-time level solution for the hydrodynamics by default. You can also use 3-time level, but just leaving it at the 2-time level gives you the option here. When I come up here to timing, the dynamic time stepping option is quite helpful on these tidally forced systems. And so we want to use the dynamic time stepping. And in order to do that, all you have to do is specify a non-zero safety factor, typically less than 0.2. So, let's 0.1, 0.2, something. Let's just start with 0.2. Now, and it's a little kind of, I don't know, confusing, but it's important that you recognize that when your auto stepping is turned on, the time step that's labeled here or shown here is actually the minimum time step allowed. So in other words, that my time step will have to be in multiples. My actual time increment for a particular time step would have to be in multiples of this value. So this tool here will initialize your time step to a pretty reasonable initial guess for what you need to make your model run and be stable. However, we might, with dynamic time stepping, we can do better than that. But what we like to use is roughly about no larger than 1/10 or even 100th of the that value for your initial time step. Now, as we run the model, I'll show you what happens, and so you can see this doesn't really affect how fast the model runs, but it is important that it actually be something relatively small that allows the EFDC model to respond to the hydrodynamic forcings that it sees. So I'll set that to 0.1 for this example for now. So with this set, all I need to do now is to tell EE how frequent I want outputs written to the linkage file so that we can display the post-processing results. By default, it's 1 day. I'm going to set it up to a 15-minute frequency. And with that set, and the timing set, we've got basically our timing here. So let's go to now the hydrodynamics and do one last little adjustment before we run the model. So here we want to assign a horizontal diffusivity, and so that we have some dampening effects that are occurring. Just this is often 0 and disabled in many models, and that works well in EFDC. It's just that makes your delta T have to be a smaller value than what you would be able to use if you include the horizontal momentum diffusion. So what we're going to use here is a spatially varying background horizontal diffusivity, and we'll just put in a 0 value here for our eddy diffusivity. So this setting here, each cell the background diffusivity will vary, and it'll be 1/1000th of the cell area is how this operates. So with that said, and again, that's more advanced training than we'll get into right now. But we'll just set these settings, say okay, we're ready to go. We're going to go ahead and save this out, and let me just save it. And it happens, it runs so fast you don't even notice it. But if we now go back here into other input, you'll now see in this, we now have a couple of other files than what we had earlier. We have a PSER file, which is the pressure time series for the open boundary, QSER, which is the river flow that we're looking at, and yeah, I think that's the main ones right now that are different as far as new files go. So with that said, we're ready to run the model. Now, the last thing that you need to do is EE will try to, if you've installed this off of a standard installation disk, EE will know where to find the actual executable for the EFDC plus code. In my particular case, because I'm a developer, I've got many versions of the executable floating around. I'm going to point to my development version here and select that. With that selected, now I can run the model. And to do that, you just click the run button here, and EE will bring up this final run dialog box. You'll notice here that this is where I specify the number of cores that I want to apply for this example. The 12 indicates that on a hyper-threaded system, I have 6 physical cores with 2 threads for each core. So in hyperthreading, so that's the reason why 2 times 6 is 12. From a maximum throughput perspective, and again, this is beyond the training we want to get into right now, for maximum throughput, generally you use half of the value of your maximum threads, which actually makes each core get used 100%. That set, look down here at the runtime status. This is going to be how information that's displayed across the screen as the model runs. I'm going to use the 1 for salinity here. That all set. We have the ability to make quick changes to some of the things we have already set. But if I do, EE will save that back out, so EFDC will use that data. Otherwise, we just leave it all alone and say run EFDC. So this is what EFDC looks like when it's running. The speed at which this is coming across the screen, I'm going to go ahead and press a key to pause it, and then you'll notice here it says if I press the same key, it will exit the model. So if I press the lowercase b now, I've just stopped the model, because what I want to do is show you how to slow that that scroll of information down. So now I'm going to press the run button again, overwrite the files that I've already generated, which are, of course, just a few seconds of runtime. But to slow that down, I just change the print interval here, and that'll make it display 10 times slower than what it was just a minute ago. So if that, hit run. So now the model looks like it's running slower, but actually it's running the same speed. It's just the frequency at which it's updating the screen. You can see here, this is time of day. This is the actual computed time step. Remember that our time step that I've specified over here was actually only 1/10 of a second, but I'm getting up to 14, 15 seconds. But the increment between any one set of or subsequent time steps can't be any smaller than the 0.1. That's why you want this number here to be small. Gives the time step resolution that you want over here as it's computing the dynamic time stepping. We've already got this model run. I'm going to go ahead and pause it, and let's look at results already that have been run. So this is a model that we have already run, same information. You'll notice here I've under the description, I've given it a project ID, given it a name for my run title, and then also my run log, which is very helpful when you're doing model calibration or scenario runs. So you can it tells the user what you did when you ran the model. So with that set, let's look at these results. So what do they look like? Water levels, elevation. So when the model has been run, you'll see here the timing frame is enabled, and the scroll bar now, you can scroll through all the time. You can use page up, page down to go to snapshots. You'll notice the time changing here as I'm pressing page down and page up. You can also go to a specific time by pressing Control G, and I can go to say exactly day 5 and see what day 5 snapshot looks like. So that's the 2D plan view. So now finally, let's go ahead and I'll load up the demo model again. And this is our history here. So the last model that I loaded, was demo 1. So reload that 1D model or 2D model. But now what we want to do is we want to go ahead and add salinity. And to do that, first thing I want to do is, since salinity is density dependent, or begins to bring density into the equations, it's also helpful when we have freshwater or saltwater interfaces to go to multiple layer analysis. So go in here to grid, and with EE, it is very easy to change from a one-layer model to a multi-layer model. All you have to do is change this right here in the number of layers. And EE has now split all the boundary conditions appropriately, and have all the rest of the model domain has all been updated based on now 5 layers instead of 1 layer. So with 5 layers set, let's go to the active module here, turn on salinity. That's all we have to do right now. We're not going to turn on any of these other capabilities. Subsequent to this webinar, we'll be talking about the adding cohesive and non-cohesive sediment transport to the Khuc model in part 2. But for now, salinity, and you'll notice that when I turn on that checkbox, that the salinity tab now is shown here on the left. Go to salinity. I want to assign my initial conditions. Again, I'll browse to a data file that contains my salinity initial conditions. And we have a range of options. I use a constant, I can use a point gridded data, or if I have vertical profile data, then I can use the vertical profiles, and EE will assign it everywhere in the domain. You'll notice that if I specify vertical profiles, that the layer options is not enabled, because it'll apply it based all your vertical and your horizontal distribution based on these profiles. But for this one, we're just going to do a simple gridded data set, and we're going to assume that it's uniform for all layers. So with that set, hit apply. It's done. Now we have assigned initial conditions in the domain. You'll see here that it reported back the average salinity for the domain. Now we need to assign boundary conditions for salinity, but because a river is, we're going to make the assumption that it comes in at 0 salinity, which is not generally necessarily true, especially for coastal systems. But for this example, let's assume that the river flow is coming in at 0, but the boundary condition at the ocean clearly gave me this message, because I have a multi-layer model now, and I tried to load up the output. But anyways, so this is the salinity in the domain. Now for the initial condition, turn off the grid. Go in here to boundary conditions and enable edit. Now I want to add salinity to this boundary. To do that, I just come up here and edit that boundary. Now in the open boundary, you can apply time series and constant concentrations. These are added together. So I could have both a constant and a time series, and it would be whatever the salinity value is in the time series at that particular time plus the constants. But this one, we're just going to go with a constant at the bottom and the surface. EFDC will interpolate the data vertically at the open boundary using this top and bottom value here, regardless of the number of cells or layers that we have. So that's all we really need to do to assign salinity at the open boundary right now for this test case. With that set, go ahead and save this out. And we'll say this is create new, demo 2. Okay, so now we have a file folder. You'll see here demo 2 has all the files, including the salt file. This is the initial condition for the salinity for all the layers. So we are ready to rerun the model now with salinity now added to the domain. Salinity is turned on. We've got a multi-layer model. We have assigned both our boundary conditions. So let's go ahead and run the model and let it go. Now, there we go. The model's starting to run. You'll notice that it starts off at that a relatively small time step here, and then rapidly begins to move faster and faster as it gets further into the domain. Because we have density turned on now, and we have a multi-layer model, you'll notice delta T is smaller. It takes a little bit longer to run, but I'll let it wrap up. So it's still only going to take, for this 10-day simulation, we're going to, 2,000 cells and 5 layers. It's going to take, roughly about 12, 10 to 12 minutes. But I don't want to wait. So I've already got the model run. Let's go ahead and load up the model. So this is the model now with the salinity turned on, multiple layers, but we have the output completely available. So I can look now at the plan view, go to water column here, salinity, and you can see the impact of tide processes. So one last thing here I want to do is let's turn on what I call timing frames. And these are really helpful when you're viewing things in 2D plan view. So go to boundary group tab here, show timing frame, and ocean. And this is the time scale. So that's 1 day of tide cycle that we're going to display. So it just kind of gives the user a sense of, or the viewer a sense of where this plan view is in the time series of the boundary forcings. And you can right mouse click on the a particular time and jump to that time in your timing frame. You can also click on it here. You can generate animations to either an AVI file or to just to the screen like we're looking at here. So this black line that you see here is actually a longitudinal section that we've cut through the model domain. And what we want to do is actually look at the longitudinal profile through there. So I'm going to press any key to stop the animation, jump back out. Let's look at this tool here, the view slice tool. And now I'm going to point to the center line file. This is that black line that was displayed there. So I'll just point to that file, hit OK, and EE goes out and matches the cells that are along that profile to the model domain, and it generates this extraction here. So this is a longitudinal profile of salinity, and this is elevation and distance from the upstream end, or distance from the first point in the polyline. This can be ordered to upstream or downstream, however the user desires, because it's really just the order in which the polyline points are ordered. So with that set, I'm going to change the axis here so that during an animation at higher flows that we're not seeing the axis change scale. So if I right mouse click anywhere over here or press one of these buttons at the top on the toolbar, I can change this to say minus 13 to 3. Whoop, that's not minus 13 to 3, 2 and 1. So this is going to be minus 13 to 3 meters in elevation with an increment of every 2 meters. Now this may be a little bit too small, so you can change fonts and everything at quite a lot of detail within the axes controls, but in order to just quickly be able to increase and decrease font sizes, you've got this button here, so you can make your fonts bigger and just makes it easier to read. So with that, I can just turn on an animation, and now we can see the tide, the salinity, the tide impacts at the open boundary. We've got the freshwater inflow coming in at the river. And with that, that concludes the model demonstration phase, and I will take questions if there are any.
All right, Paul, we have a question here. So the question is, how did you initially generate the bathymetry data for this? Was it tied to a DEM or something similar?
Yes, the original bathymetry data was developed from a combination, actually, of some more high resolution, though not multi-beam data, and then in combination with a series of cross sections that were collected at the site. So it was yeah, a combination, and we merged those data sets and generated the initial bathymetry from that. Does that answer the question?
I believe that addressed it.
Any other questions? If you do have more questions, or at least some that you may think of at a later time, you're welcome to send those questions to through the forum, or directly to EEMS, and we'll be happy to get back with you on that. As I mentioned, these files, all the files, and the presentation for building the step-by-step example for building the models will be available on our website, and we'll be sending you the files or the link to that.
All right, it doesn't look like we have any more questions, so I guess we'll go ahead and conclude the webinar. Thanks, everybody, for attending.
Thank you very much. Bye.